Okay, you've probably finished your test now and you're at your computer. What we're going to do is we're going to move into section 7.7. I'd like to save this one for the end and not put it on the test just because there's a lot of material in it. We've already had a lot through chapter 7 as it is. This deals with the polar, we're going to deal with polar, again, form, but of complex numbers. And I know it says turn to page 772, but just at some point when you're doing your homework, it goes over a nice little intro. Maybe we'll talk about it tomorrow in class. Don't worry about doing it now. But complex numbers play a really big role in electrical engineering. And if any of you ever go on to get a degree in electrical engineering, a lot of times they have to take a course in complex numbers. But this is just kind of a brief introduction. Today, we just want to talk about complex numbers geometrically, find the absolute value of a complex number, and we're going to write it in polar form and then vice versa. And then we'll kind of save the rest for Wednesday, Thursday as we move forward. All right, you should have your guided notes and the geometric representation of the complex number a plus bi. So go back to, I don't know if Algebra 2 is the first time you could talk about complex numbers. 3 plus 2i is a complex number. Is the point, basically just think of the point AB in the rectangular coordinate system. When a rectangular coordinate system is used, the plane is called the complex plane. The x-axis is what we'll call the real axis because the real part of the complex number is plotted along that x-axis. Similarly, the y-axis will be called the imaginary axis. So we're going to have a real axis and we're going to have an imaginary axis. Okay, there's our real axis. There's our imaginary axis. And now if you talk about the point, like 3 plus 2i, you'd go over 3 up 2. And as we talked about earlier, now this is kind of to the right of your guided notes. You should have that little picture above us. And then it says a complex number. A plus bi may be viewed as a position vector with initial point 0, 0 and terminal point AB. Okay, so there's your position vector. Starts at 0, 0, is going to go to AB. Now it says plot each number. They're already plotted for you, but just make sure they make sense. 1 plus 3i. As you take a look at kind of down below what we just had on your guided notes. 1 plus 3i, so you just go over 1, up 3. Negative 2 plus 2i, go over 2, up 2. Negative 3 is any real number goes on the real axis, and this will cover, that x-axis will cover all the real numbers. You can also think of it as negative 3 plus 0i. You would have 0 as the imaginary part. Negative 2i is sometimes referred to as a pure imaginary number. You can think of that as 0 minus 2i. And then point E here, 3 minus I. Okay, you go over 3, down 1. So that would be our, that's how you basically plot a complex number, same as you would a normal number. Now our imaginary axis would be the I part. Okay, the absolute value. When it's sometimes referred to as the magnitude, and we've already dealt with magnitude a lot this chapter, or a new term, modulus. Okay, so the absolute value is synonymous with the modulus. A lot of times complex numbers will be given just the z as as a term to represent it. So z equals a plus bi. The absolute value of the modulus, we use our absolute value bars, is simply the square root of a squared plus b squared. It's going to be the length. Okay, it's no different than the magnitude that we did before. You create a right triangle, a squared plus b squared. Okay, now find the absolute value for each complex number. All right, well, we want to know the absolute value of 4 plus 3i, and that's simply going to equal the square root of 4 squared plus 3 squared. Do not put the I there. Okay, so if we go back here for a second, it is just a squared plus b squared. We do not put the I because squaring that would end up changing the sign of that second part. It's going to be 16 plus 9, square root of 25, which is 5. So the modulus for the absolute value is 5. B, absolute value of 2 minus 3i. It's going to be the square root, 2 squared, plus negative 3 squared. We're going to end up with the square root of 13. So there's our absolute value or magnitude. Okay, polar form. That's rectangular form. A plus bi is rectangular form. We can also talk about the polar form. Just like anytime you have a regular coordinate, you can convert it to polar form. We can take a complex number and convert it to polar form. Its polar form would be right here. Z equals R times cosine theta plus I sine theta. Well, R is your modulus, your magnitude. A is going to be R cosine theta. B is R sine theta. R is square root of A squared plus B squared. And tangent of theta equals B over A. Again, I like to talk about the reference angle. And I'm going to put absolute value around that because it's going to depend on what quadrant we're in. When a non-zero complex number is written in polar form, the positive number, as I said earlier, is the modulus or absolute value of z. The angle is called the argument. Okay, so that's a little bit new notation there. Theta equals the argument of z. Okay, that is the angle, the direction angle. All right, I think we're on the back of those. Let's see here. All right, we're on the back of those guided notes. And actually, I'm going to do two of them. I'm going to do A, where Z equals 1 minus square root of 3I. And then B, I'm going to do, it's not on there. I'd like you to add it. Z equals, not negative. We're just going to go ahead and do 5I. Okay, now for Z equals 1 minus square root of 3, we need R value. R equals square root 1 squared plus negative square root of 3 squared. That is 1 plus 3, which is square root of 4, which equals 2. So that's your R value. Well, just think about where this point is. 1 negative square root of 3. It's got to be in quadrant 4. Okay. We're going to find that reference angle. Reference angle equals inverse tangent, absolute value, and I'm just, normally I'd put negative there, but since I'm taking the absolute value, I'm just going to drop that over 1. All right, let's see here. I'm going to go ahead and pull out my calculator in case I need it later. Okay, so I'm going to do inverse tangent, square root of 3, inverse tangent, square root of 3, and you get 60 degrees. Well, that's my reference angle, so the actual angle will be 300, and this is how we're going to write this. Z equals 2 cosine 300 degrees plus I sine of 300. Okay, so there's your complex polar form of that complex number. It's basically exactly the same as converting rectangular to polar. All right, z equals 5i. Where's that at? So I just want to make sure you understand where that's at. That is going to be on the y-axis, on the imaginary axis. Well, if you kind of go through the steps, you should be able to tell me what the polar form is. But if you go through the steps and you just kind of get lost in the work, you're just going to think of this as 0 plus 5i. 0 squared plus 5 squared is going to be square root of 25, which is 5, so z equals 5. If you try to find the reference angle, you're going to do the inverse tangent of 5 over 0. Well, if you try that, inverse tangent 5 divided by 0, it's going to give you an error. I can't divide by 0. Well, it does have an angle. It doesn't have a reference angle because that angle right there is going to be 90 degrees. Okay, when you take the inverse tangent of something over 0, we get is undefined at 90 degrees. And so our polar form will be 5 cosine of 90 degrees plus I sine of 90 degrees. Now, it was absolutely fine if you just went straight from the point to here if you understood how it was set up. That's absolutely fine. All right, last one. We're not going to finish the guided notes. We're just going to do this one. And this is going the opposite way. Write the complex number in rectangular form. Rectangular form for complex numbers a plus bi. And typically we put the constant in front of the I in rectangular form. A lot of times it's easier to put it, you're going to see it written as I sine of 150 when it's in the polar form. Well, in this case here, A is going to equal 6 times cosine of 150 degrees. B is going to equal 6 times sine 150 degrees. All right, so if you remember our basics, if that's 150 degrees, that's 30. Cross from that's 1/2. And we need to take into account that'd be negative radical 3 over 2. So it's going to be 6 times negative square root of 3 over 2. 6 divided by 2 is 3. It's going to become negative 3 square root of 3. B is going to be 6 times 1/2 because that's the sine of 150. So that's going to be positive 3. And so now my final answer in rectangular form is going to be negative 3 square root of 3 plus 3i. Okay, negative 3 square root of 3 plus 3i. All right, that's done. Very similar as converting it with just from rectangular to polar. Okay, now we're just dealing with complex numbers in the same concept. All right, we'll hit this stuff tomorrow. I'm not going to assign any homework. Just get this done. Get your guided notes done. If you do get a second, turn in your book. Anybody interested in electrical engineering or knows anything about it, you might go to page 772 and read up on the little blurb there. All right, you guys have a great day. No homework. We will see you on Wednesday.